Hello, this is the section 14.5 to 14.6 lesson on the topic of similarity. Now, this topic of similarity is at first glance going to look a lot like the topic of congruence that we talked about in section 14.3. So let's review the definition of congruence. And here was the informal definition. Two shapes that are the same size and shape are called congruent. So as an example, if we start off with this shape and we just slide it over to get a new shape, well, this new one is the exact same size and shape as the original, so it's congruent. Likewise, if we rotate that shape around a point 90 degrees, we get a new shape. We haven't changed the size or the shape, and so this is congruent to the second one, which is congruent to the first one, so they're all three congruent. In section 14.3, we also talked about some triangle congruence criteria, such as side, 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 which said that if two triangles have the same length sides, then they're congruent. Another one was angle, side, angle. So as an example, here we've got two triangles, a top and a bottom, that share an angle of 40 degrees, a side there of this red side, and then an angle of 60 degrees. So those two triangles are congruent. Another one was side, angle, side. We said that if two triangles share a side, an angle, and then a side, they're congruent. So here these two triangles share the red side, an angle, and then the green side, and so they are congruent. And so similarity is going to, at first glance, look a lot like congruence, but there's some key differences, and we're also going to see some similar looking triangle criteria. So let's define similarity, and we'll define it informally, and then later we'll define it a little more formally. So informally, two objects are similar if they have the same shape, but not necessarily the same size. So notice that here they have to share the same shape, but not necessarily the size. For congruence, they have to share a shape and a size. So for instance, here's a picture of a house. Notice that they have the same shape, but this one's obviously bigger than this one. So these two objects are similar. Here's two pictures of a bunny. They both have the same general shape, but obviously this one's bigger, and so they are similar. Another way to think about similarity is that the two pictures are either scaled up or down versions of each other. So this house here is just a scaled up version of this house. This bunny is a scaled up version of this bunny, so they're similar. Another word for similarity is called geometrically similar. Here's some examples of non-similar objects. Here's our original bunny. Here's a kind of a squished bunny. Notice that's the same height as this original bunny, but it's got a lot narrower face. So we've changed the shape, so this bunny is not similar to the original bunny. Here's another one where we've kept the same width, but the height is smaller. And so this bunny obviously looks a lot different than this bunny, and so this bunny is not geometrically similar to the original bunny. Okay, so let's think about a little more formal definition of similarity, and let's try to motivate this definition with a couple of examples. So here's a rectangle A and a rectangle B. This rectangle B appears to be a scaled up version of this rectangle A. So let's think about how could we go from rectangle A to rectangle B. Well, let's look at their short sides. We went from 2 to 4, and the long sides went from 5 to 10. So to go from A to B, we simply multiplied each side by 2. Well, let's give that number 2 a name. We're going to call it K, and K is also called the scale factor. And so that leads us to a little more formal definition of similarity. It says that two objects are similar if each dimension of one object is multiplied by some constant k to get the dimensions of the other. So if all we did was multiply each dimension by some constant k to get the other, then the two objects are geometrically similar. Now k doesn't necessarily have to be a whole number. It could be a decimal or a fraction, but as long as we multiply every dimension by the same constant k, then we're going to get two geometrically similar objects. So let's do a couple of examples of using this definition. Here are two geometrically similar rectangles. Let's find the value of k. And so let's think about the short side here. And so we need to go from 8 to 5. So we think, what do we need to multiply 8 by to get 5? Well, we could multiply by 5 over 8, right? Because if we multiply if we multiply 8 by 5 over 8, the 8's cancel, we're going to be left with 5. That's exactly what we want. Now, let's think about the long side. We need to go from 16 to 10. So we need to multiply by 10 over 16, and that fraction reduces to 5 over 8. And so for both the short and the long side, k is equal to 5/8. And so there's our value of k. Let's do another example where we ask a little different question. Are these two rectangles geometrically similar? At first glance, they appear to be just scaled up versions of each other. So we might think the answer is yes, but let's confirm. Glance at it. Now, the first two examples dealt with rectangles, but geometric similarity can apply to other shapes like triangles. So are these two triangles similar? So we're going to answer this in the same way as the previous question, except that now we've got three sides to deal with rather than just two. So let's break this up into a left, a right, and a bottom. And so on the left side, we need to go from 10 to 20. So 20 over 10 is 2. On the right, we need to go from 5 to 10. So we need to multiply by 10 over 5, which is 2. And in the bottom, we need to go from 12 to 24. So multiply by 24 over 12, which is 2. So k is the same for all the sides. So the answer is yes, they are geometrically similar. Here's another example, a little different question. Find the value of x in the following similar triangles. So we're told that we have two similar triangles. That means that this triangle is just a scaled up version of this triangle. We're told that this bottom side is 3 and this bottom side is 9. This is our unknown. This is 6. Now we're not told the lengths of those long sides, but that's not really important. So there's maybe several ways we could go about solving this problem. I'm going to illustrate just one way in this lesson. The book will talk about some other ways of solving this. But let's try to find the value of k. And let's look at just the bottom side. So I need to go from 3 to 9. So multiply by 9 over 3, which is 3. So there's the value of k for those two geometrically similar triangles. Now I don't need to consider the other sides at this point to find the value of k, because I already know they're geometrically similar, so I only need to look at one side. So now to go from this side x to this side 6, I need to multiply x by 3, and that's going to equal 6. So now I've got an equation here. I can do a little bit of algebra to solve for x. If I divide both sides by 3, I get that x is 6 over 3, which is 2. And so there's the answer. The x is equal to 2 feet. Now our previous examples dealt with simple geometric shapes, rectangles and triangles namely. Here's an example that applies to an object with a very irregular shape. Suppose an artist creates a scale model of a sculpture. The scale model is 10 feet wide, 20 inches tall. If the actual sculpture is to be 60 inches wide, then how tall will the actual sculpture be? So here's a picture of our scale version. Here's a picture of the full large version. So notice that those are not rectangles or triangles or any simple shape, but that's okay. They don't have to be simple shapes. All we need to know is that they're scale versions of each other. This is just a scaled up version of the smaller one. So that means they're geometrically similar. So we can apply the same basic ideas from our previous two problems. In this problem here, we know the height and the width. Over here, we know the width, but we don't know the height. So the first thing that we need to do is find the scale factor k. And so we can look at the bottom. To go from 10 to 60, we multiply by 60 over 10, which is equal to 6. And so now to go from 20 to question mark, we need to multiply by that same number 6. 20 times 6 is 120. And so there's our answer. The full sculpture is going to be 120 inches tall. Now we saw some criteria for angle congruence. Now we're going to look at one criteria for triangle similarity. And this is called the angle, angle, angle criterion. And it says that triangles with equal corresponding angles are similar. So here's a couple of examples. Here's a 30, 60, 90 degree triangle. Here's another 30, 60, 90 triangle. And so these two triangles are similar, is what this criteria is saying. They're not congruent, obviously. This one's bigger than this one, but they are similar. This one here is just a scaled up version of this one. Here's another example. We have a triangle with a 30 degree angle, a 50 degree angle. And the last one isn't given, but we could easily calculate that. We know that the sum of the angles in a triangle is 180. 30 plus 50 is 80, so that means this angle here has got to be 100. Here's another triangle with an angle of 50 and 30, so by similar reasoning the other angle has got to be 100, and so these two triangles have the same three angles, and so they are similar. Now one thing that this second example here illustrates is that in order to apply this criteria, we don't really need to know all three angles. We really only need to know that two angles are equal. If we know two of the angles, we can determine the third. And if we know that two triangles have two equal angles, then that means their third angle is going to be equal, and so they are similar. So let's look at a couple of applications of this angle, angle, angle similarity criteria. And these examples apply to parallel lines. And the point that I want to make here in this example and the next is that the parallel lines often lead to similar triangles. So here's a nice picture where we got a line here, BC, and another line, ED, and we're told that those are parallel. Now if we cut those lines with a couple of other lines, like this line here and this line here, that forms two triangles, ABC and ADE. Now if we look at like these angles right in here, well these are just opposite angles, and so they're going to be equal. And then we've got, look at this angle here and this angle here. Those are both formed by this one line that crosses parallel lines, and we know that angles, or excuse me, lines make the same angles with parallel lines, and so that means this angle here is going to be equal to that angle there. And so we've got this big triangle here and this small triangle here. They share two angles, and so by our angle, angle, angle criteria, we can say that this small triangle ABC is similar to this large triangle ADE. So there we started with two parallel lines. We formed a couple of triangles with those parallel lines, and those two triangles are similar. Here's another example. Let's say we got this line here and this line that are parallel. We're going to cut those with a couple of other lines to form a small triangle ABC and then a large triangle ADE. And in those triangles, obviously they share this angle right here in common. And if we look at these angles here, well they're also going to be the same because we got parallel lines that are cut by a third line. and so those angles are equal. And so we've got this small triangle and this large triangle that share two angles, and so those two triangles are going to be similar. Specifically, ABC is similar to the large triangle ADE. So let's look at an application of this idea that parallel lines often lead to similar triangles. And let's find the height of the flagpole in the figure below. So we've got a flagpole here sticking in the ground, and we like to determine its height. Well, we've got the sun shining down, and this sunlight we can represent as by these rays that form a lot of parallel lines. And so the sun hits this flagpole, and that creates a shadow. And we can easily measure the length of that shadow, and let's suppose that length is 7.65 meters. Well, now over here, we've got a picture of a meter stick stuck in the ground, and that also forms a shadow, and let's say that shadow is 1.2 meters long. Well, we got here is a bunch of parallel lines, and we got two triangles here, and so by our similar reasoning from before, those two triangles are going to be equal. Are going to be similar. Excuse me, they're going to be similar triangles. This here is just a scaled up version of this small triangle right here. And so what we'd like to know is the length of this one unknown side. Well, that's basically the same problem that we did before. So again, we've got similar triangles, and let's find the scale factor k. So let's look at the bottom side here. To go from 1.2 up to 7.65, I would need to multiply by 7.65 over 2. Do that arithmetic, I get 6.375. So there's my scale factor k. And so now let's look at this this other side. To go from 1 meter here to this unknown distance, I would need to multiply 1 by the scale factor 6.375, and do that arithmetic, I get just 6.375. So there's our answer. Our flagpole is 6.375 meters tall. So there's a simple application of similar triangles and parallel lines to find the height of a flagpole. Now, one observation here is that these examples that we've done only dealt with lengths, and we went from length in one similar object to the length in another similar object by multiplying by k. In our next example, we're going to look at areas, and then lastly, we're going to look at volumes to see how things are similar and how different. So let's look back at this first example of these two similar rectangles A and B, where our scale factor k was equal to 2. Now let's think about areas of these two rectangles. The area of rectangle A is just 2 times 5, which is 10, and the area of B is equal to 4 times 10, which is equal to 40. Now we might be tempted to say that, well, if k is equal to 2, then that means the area of B is going to be just twice the area of A. But if we look at these two numbers here, what we see is that the area of B is not twice the area of A. It's actually 4 times the area of A. So the area of B is equal to 4 times the area of A. Now let's make an observation there. 4 is equal to 2 squared. Now where'd the 2 squared come from? Well, the 2 came from k equal 2. And the square is basically due to the fact that we're dealing with area, which has units of like feet squared or meters squared. So to generalize this example, what we've illustrated is that to find the area of a similar object, we multiply the original object by k squared. We don't multiply by k, it's k squared. So let's look at an application of this observation. If there were a new Goodyear blimp that was 2.5 times as long, 2.5 times as wide, and 2.5 times as tall as the current one, then how much paint would be needed to paint the new blimp compared to the current one? So here's a simple picture of our original blimp and our new bigger blimp. And so if we wanted to paint it, how much more paint is it going to take? We might be tempted to say, well, it's going to take 2.5 times as much paint because the new one is 2.5 times as big as the previous one. But we got to be careful about this. So the first thing that we need to realize is that when we're talking about paint, we're really dealing with area. So we're asking how much more area do we have in the new blimp than the old one. And so let's use the idea that we just developed, that the area of this big geometrically similar blimp is equal to k squared times the area of my original blimp. It's not just, we don't just multiply by 2.5, we multiply by 2.5 squared. So if we do that arithmetic, we get 6.25. And so the area of the big blimp is 6.25 times the area of the small blimp. And so our final answer would be is that it would take 6.25 times as much paint to paint the large blimp as the small blimp. So it's a lot more than just 2.5 times as much. It's 2.5 times squared, or 6.25. Now let's think about volume. And here are two geometrically similar cubes, 4 by 4 by 4 and 8 by 8 by 8. And so we can easily see that here the scale factor is k equal 2. And let's think about the volumes of these two cubes. We might be tempted to think that this bigger cube has a volume that's just twice the original cube, but let's see if that's the case. Well, the volume of the small cube is 4 times 4 times 4, which is 64. The volume of the big cube is 8 times 8 times 8, which is 512. Well, 512 is obviously a lot bigger than twice of 64. In fact, 512 is 8 times 64. You can verify that on your calculator if you want. Now, what's significant about 8? Well, 8 is 2 cubed. Where 2q comes from? Well, 2 is k, and cube is due to the fact that we're dealing with volume. The volume is, in this case, would be inches cubed. Just like when dealing with area, we multiplied by 2 squared, because area was like square inches or square feet or whatever. So to generalize this example, what we've illustrated is that to find the volume of a similar object, we multiply the original volume by k cubed. If we don't multiply by just k or just k squared, we got to multiply by k cubed. So let's look at an application of this. Same scenario where we've got this new blimp that's 2.5 times as big as the small blimp. And here's the question. How much gas would be needed to fill the new blimp compared with the current one? And we're going to maintain the same pressure. So we might be tempted to say, well, it's going to take just 2.5 times as much gas to fill the new blimp. But we're not dealing with just a single dimension here. We're dealing with volume. So as we just illustrated, the volume of our big geometrically similar blimp is going to be k cubed times the volume of our smaller geometrically similar blimp. So 2.5 cubed comes out to be about 15.6. And so our final answer is that it would take about 15.6 times as much gas to fill the large blimp as the small blimp. So a lot more than just 2.5 times. It would take about 15.6 times as much gas. So that's it for this lesson. Your assignment is to read sections 14.5 and 14.6.